Hello, welcome to NPTEL online certification course on Introduction to Application of AI to Robotics. Today we are going to talk about modeling and control of a single joint. In the last lecture, we have seen some basic principle of the control, and that we explained by taking an example of a second order system, simple spring mass damper system, and we studied the concept of the simple control. Okay. So, I expect that by end of this lecture you will able to understand how can we model a single joint of a manipulator. So, here are the contents. I will introduce the topic to you, then we will see the DC motor at a joint, and then effective inertia, what are the role of unmodeled flexibilities, and how can we estimate the resonance frequency, and then the final closed loop system equation, and I will be illustrating some of the example with Python. Okay. So, you see a robotic manipulator consists of number of joints. Okay. So, for example, in this humanoid, say we have number of joints, right? Say for example, 3 degree of freedom shoulder joint, then 1 degree of freedom elbow joint, 3 degree of freedom wrist joint, and so on. Okay. So, we will try to understand how can we model simple one joint, okay, so that the analysis is very simple. And you see robot, those who are having the multiple degrees of freedom, so that single joint is going to be repetition, okay, at the other degrees of freedom, alright. So, with reasonable assumption, the system behaves like a second order linear system. That is why in the last lecture we have seen a lot more in detail the second order linear system, okay, and the joint is driven by an actuator, and usually we use the DC motors basically for the actuation purpose, because it has got the advantage that it is easy to control. Okay. So, here is a cut section of the DC motor, okay, which is from the Maxon one. This is the output shaft, okay, and this output shaft is attached to the gearbox here, the reduction gear head. And before gear, so we have the ironless winding here, then we have the magnet, here we have the commutator, and we have the brushes, and at the back of it we have an encoder in order to measure the speed. Okay. So, this is the arrangement in a motor, and so the stator of the motor has ironless winding, okay, and it is a stationary part basically, and it creates the magnetic field. Okay. So, we may have the permanent magnet or we may have the electromagnet. Okay. And then we have the rotor part, which is also called armature, that rotates with the shaft and it carries current through the winding. Okay. And the commutator, it has got role of switching the current direction, and it ensures that torque remains in the same direction. Okay. So, here the force generated is given by charge times velocity, and it is a product with the magnetic field. Okay. So, basically through current, the magnetic field, and then we get the force and we get the torque. Okay. And you know that the moving charges with velocity in an electric field experiences force. Okay. So, coming to the DC motor as a joint actuator, okay. So, what we have is actually we apply a voltage to the motor, and it goes to the armature circuit, produces a current, then we get the torque generated, which is Km times the current in the armature. So, you have the joint output, and so we get the angular velocity, and we have the back EMF, and this back EMF in fact reduces your applied voltage. So, that we will be seeing how it is. So, the torque generation is given by a constant times current through the armature, okay, and the back EMF is again a constant times the angular velocity of the motor. Okay. So, these Km and Ke, these are called the motor constant. Okay. So, here is a schematic of your motor where you have a voltage source. This Ra represents the resistance of the armature, La represents the inductance of the armature, and here your bushes are indicated basically, and you have the power through the shaft from here. Okay. So, this is say the back EMF generated. Okay. Then I can write the Kirchhoff equation here. So, that will be the voltage across the inductor plus the voltage across the resistor, and that is going to be equal to the voltage supplied to the circuit, which will be Va minus the back EMF. Okay. So, this way we can write the expression for the current through this circuit. Okay. Alright. So, this is the armature voltage equation, and inductance makes the current change slowly. Okay. So, that motor current cannot jump instantly, but the motor torque is indirectly limited by how fast the current can rise. And in current drive system, the driver adjusts Va, okay, to force the desired armature current. Okay, that is what we have defined as Ia. Alright, so next let us see that what is the role of gearing in effective inertia. Okay. So, suppose this is your drive system. Okay. So, you have a motor, alright, say the torque generated by motor is tau m, inertia of the motor is represented Im, and let us say there is some frictional resistance present, okay, that I am indicating by the say frictional coefficient Bm, and the angular velocity of the motor shaft is theta m dot. Here we have the gearing. Okay. So, say the gear ratio is eta here, and this is driving a load here which has got inertia I, and velocity theta dot, and of course, some friction present in the system, that is represented by B here across the load side. Okay. So, here you see in the gear we know that we are going to have the amplification of the torque, right. Okay. So, here if eta is the gear ratio, the torque at the load side is going to be eta times that of the motor torque, and angular velocity is going to be reduced here. Okay. So, theta m dot by eta. Okay. Here I am assuming that my eta is greater than 1, as you can see also in this figure. Okay. Now, if we see the torque balance at the motor side. Okay. So, you see this tau m has to drive what? It has to drive this inertia. Okay. So, Im theta m double dot is going to be the torque, and then it has to overcome this friction. So, you have Bm theta m dot, and then this load side. Okay. So, the load side inertia and load side resistance because of the friction present over there. Okay. And this we have to divide by gear ratio because we are calculating towards the motor side. Okay. So, now in this equation, if I substitute for say theta m double dot from here, okay, and as well as for the theta m dot, I can simplify that like this. So, here I have substituted for theta m double dot, which is going to be your theta m double dot, that is going to be equal to what? Eta times theta double dot. So, that I substitute here, and here the theta m I substitute here, and this portion I keep as it is. Now, what I do? I combine the theta double dot term. So, it is here. So, you have Im eta plus I by eta plus I segregate the theta dot term. So, I have Bm eta plus B by eta. Okay. So, here let us further simplify, take eta towards left hand side. So, this is eta tau m, and this is theta double dot, Im eta is square plus I, and here Bm eta is square plus B, that is there. And so, this eta times tau m, this is my tau. So, this tau is this equation. Alright. Now, here this term, so this is my torque, what? It is at the load side. Okay. So, this is equal to some effective inertia times the angular acceleration of the load, and this is the effective damping or say frictional force into the velocity of the load. Okay. So, this is what effective inertia is defined and this is what effective damping is defined. Okay. And you see here there is one thing which we have to prominently note down, and that is that if my eta is going to be very much larger than 1, okay, then what will happen? If this value is going to be very large than 1, then we are taking the square of that. Okay. So, that value is going to be still higher. Alright. So, with that what happens, the significance of this term here in the inertia and B in the damping reduces. Alright. So, hence with higher gear ratio, okay, effective inertia becomes almost constant, that is it is not depending on the load inertia. Okay. And that is one of the advantage of the higher gear ratio. Okay. To have a feel of this one, let us see an example where I say that my I varies from say 2 to 6 and I have the motor inertia this one and gear ratio 30. Say what is the value of the effective inertia? It is a minimum and the maximum value. Okay. So, if you see that the minimum value of I is 2, maximum is 6 and this is the gear ratio is square, this one. Okay. And here I have got the motor inertia. Okay. So, you see that these values are 11 and 15 which are far more than this value, the 2 value. So, 11 is far more than 2, similarly 15 is far more than 6. So, this is what I was saying, okay, that is because of higher gear ratio in the motor, okay, the role of load inertia reduces. Okay. Alright. Next let us see unmodeled flexibility. See, we assumed everywhere, okay, that our elements, okay, say whether it is a gear, whether it is a shaft or bearing, okay, all are driven like rigid links. But you see in reality all these elements have finite stiffness. Okay. So, your flexibility, if you want to model it, your order of the system is going to increase and your analysis is going to be much more difficult. Okay. So, the natural frequency of the unmodeled resonances, if they are very high, then we can neglect their effect, okay, as compared to the influence of the dominant second order pose that we have modeled in the system. Okay. And since as we will be going through, okay, we have chosen not to model the structural flexibilities in the system. So, we must be very careful that these frequencies are not excited. Okay. So, we must be careful not to excite these resonances, right. Okay. So, there is a thumb rule. Okay. So, the thumb rule to limit the closed loop natural frequency is that closed loop natural frequency that should be less than or equal to half of the your lowest structural resonance frequency. Okay. So, that thumb rules helps, okay, in your design. Now, you see if we increase the gain as we have seen in the previous lecture, okay, we have a faster response, okay, and we have the lower steady state error that is there. But too high gain, okay, may excite unmodeled resonances and also very high gain makes your system unstable. Alright. So, there could be criteria to get the gain values, alright. What should be the gain values, alright. So, that we can get by taking analogy from this control law expression and from the second order system, okay. This omega n square as Kp here and your omega n as root of Kp. Okay. Let us take an example for this. In a simple spring mass system, suppose we have the unit values for mass, stiffness and damping and your resonance frequency is say 8 radian per second. The question is what is the value of that alpha and beta which are used in the control law partitioning which we have seen earlier. Okay. So, find the alpha beta and the gain value Kp Kv for position control law so that the system is critically damped, which of course we always want to. okay, and they do not excite unmodeled dynamics and has a high closed loop stiffness as possible. Okay. So, here we have the alpha and m is equal to 1 and beta we have seen is bx dot plus kx. So, if we substitute value of b and k, I have x dot plus x, and this omega n has to be less than or equal to resonance by half. So, from here I can get what will be the value of omega n. Okay, the resonance is 8. Okay. So, here from here I can get omega n as 4 radian per second. So, my Kp will be omega n square and Kv will be 2 root Kp. Alright. So, this is what we have seen for the critically damped system. You can correlate this with the previous lecture. Okay. Next, let us see that is there a way to estimate the resonance frequency? Okay. So, for every source of structural flexibility, an approximate analysis of the resulting vibration is possible, of course, that we can do. Okay. We can describe the effective mass or inertia of the flexible member. Okay. So, the flexible member can be approximated, we can approximate by simple spring mass system, then I can describe the natural frequency as root of k by m. So, this way we can estimate the natural frequency. Alright. So, let us take an example, say we have a massless shaft with k is given and inertia is there. If the shaft stiffness was neglected in the modeling of the dynamics, what is the frequency of this unmodeled resonance? Okay. So, this one we can simply get by root k by m, alright. So, it is 20 radian per second, and if I divide this by 2 pi, I can get it in terms of the hertz. So, that will be around 3.2 hertz. So, this way we can evaluate the omega resonance. Okay. So, for estimating resonance frequency, we can do some approximation. Okay. So, we can have a lumped model, okay, that can be used to estimate the mass or inertia of the link. So, for example, if you have a beam over here and in which the mass is distributed, its effect can be taken, okay, as say mass of 0.23 m at the tip, and then your force is applied over there. Okay. So, this has been done. Similarly, if you have a shaft, okay, the effect of distributed inertia can be modeled as a lumped inertia with the inertia here taken as 0.33 I. Okay. So, this way we can do the approximation by lumping the parameters. Alright. So, let us take an example here. Suppose a link has a mass this much and has a endpoint lateral stiffness this much. Assuming the drive system is completely rigid, the resonance due to the flexibility of the link will limit control gains. So, what is the omega resonance? Okay. So, in this case we can find out the m effective, which is this one, and then simply we can get omega resonance as root of k by m. Okay. So, this will be in the term of the hertz. So, the final closed loop system equation, okay, similar to the spring mass system, a single joint of a manipulator can be controlled with the partition control law, which is given by alpha as I max plus eta square Im, beta as b plus eta square Bm into theta dot, and so your tau dash is going to be theta d double dot plus kve dot plus kpe, and the resulting system control loop dynamics will be this one, okay, and this will be equal to the disturbing torque. Okay. So, this relation, how from this equation to this equation we have come, that we have seen in the previous lecture. Okay. So, those who are getting any doubt, please refer to my previous lecture, and here the gains chosen Kp and Kv this way, or considering the structural flexibility. So, to understand in a broader way the control of a single joint, okay. So, suppose I have got a joint or link and at that joint I have a motor and the motor rotation is theta, okay. So, through an encoder we get this theta value. This theta value I provide to the summer here where we have the reference coming, alright. So, we get the error here and this error is supplied to the PID controller, and PID controller generates the torque, okay, torque, and that is given to the motor driver, and through motor driver it goes to the DC motor, okay, and this DC motor drives your joint or link, okay. So, this way you have the control of a single joint, alright. So, as I just explained, you have the desired angle, you get the error through feedback, then you have a corrective torque, and then you get the actual angle, and then again you have the feedback. And if a manipulator has got many degrees of freedom, then or many number of joints, then this is going to be repeated for the each and every joint. Okay, here is the examples using Python which you can practice and see, okay. So, modeling the torque balance equation with no load, okay, say this expression I want to model with no load. So, I define Im, Bm and tau m, okay. So, that I am defining here, and here is the this equation being written here, alright, and then theta dot, and then here evaluation of I effective, B effective is done, okay. So, this is the theta double dot, alright. So, this way we can write that, and here basically we are doing for the no load, we are integrating here this equation, that is theta double dot, and we are getting the theta dot for the motor here, okay, and theta double dot for the motor is here, okay. So, this way we can get that. This is done for the no load one, and yeah, okay, and we are taking gear ratio as 1 here. So, this is the plot basically, okay. So, here are the values, say tau m, Im and Bm, steady state speed is this one, okay, and so this is the angular acceleration which we get, okay. Then let us see the effect of the gear, okay. In order to see that, I take a value of say eta is equal to 10 here, okay, and put up these equations in terms of the eta. So, here are the plot for the angular velocity and the torque, okay. So, here if you look at, this is the motor velocity, and this is the your load velocity. So, with a gear ratio of 10, this is 20, okay. So, for the 10 at the load side, the velocity is going to be 2 around. So, this will be 2 radian per second. Likewise, if you look at the torque amplification, here the motor torque is 2, and if your gear ratio is 10, you are going to have the 20 Newton meter torque here. Okay, here is the effect of gear ratio on the motor speed, okay. So, again we define I and B over here, and we are trying to see this with the various gear ratios, say 1, 5, 20 and 50. So, you have gear ratio 1, 5, 20 and 50 over here. So, here I am looking at the motor angular velocity, okay, that is at the motor side with the time. So, you can see that as your gear ratio increases, your motor angular velocity also increases. This we are seeing it at the motor side, okay, and here is the code for solving the ODE for the load speed, then extracting a load speed and convert it to the motor speed, and calculating the effective load inertia here and steady state load speed here, okay. Next is the effective inertia. Again, of course, this we have seen in the earlier example also, and here also we can see that with the various gear ratios how the effective inertia values changes, okay. So, here you can see that effective inertia over here and here with the gear ratio, okay, how that is changing. Similarly, with the change in gear ratio, how the effective damping is getting changed, okay. So, again these are tabulated over here and they are shown in the plot, okay. And you see that high gear ratio, the effective parameters grow quadratically, right, meaning the motor's own inertia start dominating the system. This is what I explained you in the previous slides. So, to summarize, what we have seen that the robotic joints are modeled as a second order linear system driven by the DC motors, okay, And the DC motor consists of, you have a stator, you have a rotor, you have commutator, okay, which ensures unidirectional torque, and the motor armature inductance is often neglected for simpler transfer function modeling. Okay, those who have studied the Laplace transfer functions, they can appreciate it in a much better way. What is the role of neglecting the armature inductance? Then the effective inertia combines motor and load inertia is scaled by the square of the gear ratio, that also we have seen, and with high gear ratio the effective inertia grows quadratically, causing motor inertia to dominate. The real joint have unmodeled flexibility in say gear, shaft, bearing, okay, which introduce high frequency resonances, and these resonance frequencies must be estimated and avoided to prevent exciting unmodeled structural modes. Okay. And you see the final closed loop equation integrates torque balance, gear relation and the effective inertia terms, and we have seen some of the Python simulation which illustrate the effect of gear ratio, motor and load speed and step response behavior. Okay. So, these are the references which you can see, okay, for the reading, and with this I would like to say thank you. See you in next lecture.